So in this question, we're looking at the use of complex numbers, and I think with Mike Betts, you're probably looking at it in terms of an electric circuit, not necessarily what you're going to be doing in the exam, but let's just look at this question and then I'll give a few more little indications. So first thing is, well, can we add or subtract complex numbers? That's very easy to do. If I'm adding complex numbers or subtracting them, I keep the real parts and the imaginary parts separate. Remember, j is the imaginary number, so j actually means the square root of -1, which is something that cannot be calculated in the real world. So that's why we talk about it as being an imaginary number. The fact that it's an imaginary number is unimportant. It's just that it's a very useful way of representing two-dimensional objects, vectors in other words, in engineering. So we use complex numbers for that reason. So all I do to add these two together, or subtract them, would be to add the real parts together. So 4 plus 3 is 7. And add the imaginary parts together. Minus 6j plus 1j. There's no number in front of the j, so that means one lot of j is minus 5j. So almost think of it like x's. Minus 6x plus x would be minus 5x. In the same way, we'd end up with minus 5j. So that would be what we'd get if we were to add these things together. Now, for this particular question, you're asked to find the magnitude of the current and its phase relative to the voltage. So what I need to do is to use Ohm's law to find I, and that's V over R, or Z if we're talking about an AC circuit. So that's going to equal the voltage, which is 20, divided by the impedance, which is 7 minus 5j. So you've got to divide one number by another number. So to do this, we have a complex numbers, well, effectively a real number divided by a complex number here. So we have to do division. And one way to do division is to turn these numbers into polar coordinates. So everything is taken as an angle with reference to 0 as the voltage. So this has an angle of 0, so the voltage is 20 angle 0. The symbol here means angle, over. Now we convert this number, 7 minus 5j, into polar coordinates on the calculator. If you look at your calculator, above the plus button it says POL, which means polar. So if we're converting to polar, that's the button we want. If we're converting from polar to what's called rectangular, then we want the minus button, which is next to it. So we want to convert 7 minus 5j to polar. And so we hit shift and then polar on the calculator. And then it gives us POL and open brackets. So then we put our coordinates in, 7. And then it's after a comma for the next coordinates. And the comma is above the close bracket symbol. So you press shift close bracket, and that gives you a comma, and then put minus 5 in, using the minus button top up on the left hand side there, the minus in the brackets, minus 5, and then close bracket, and then hit equals, and you get the answer. Now if you want the answer in radians, which we sometimes want, or degrees, you need to make sure again you're in the right thing on the calculator. So if in degrees, you'll get R, which is the number in front of the angle, and then the angle following on. So if I scroll along, it tells me that theta is minus 35.5 degrees. So that's converted this to polar. And now to do the division, I'm actually going to be doing the current equals 20 angle 0 divided by 8.6 angle minus 35.5 degrees. And when we divide in polar, we divide the numbers, so it's 20 divided by 8.6, and we subtract the angles. So that's going to be 20 divided by 8.6, which is 2.3, near enough. We rounded to two significant figures. Angle 0 minus 35 is plus 35, so that's 35.5 degrees. And that will be my final answer. And the power of this is that in electronics anyway, this gives me the size of the current, 2.3 amps. So we've got a current of 2.3 amps flowing, and it's out of phase, it's leading, because it's a positive angle, by 35.5 degrees. So that would be my answer, that the current is 2.3 amps leading by 35.5 degrees. So we can add and we can subtract, we can multiply in polar form and divide in polar form quite easily. To multiply in polar form, you multiply the numbers and add the angles. To divide, you divide the numbers and subtract the angles. A bit more complex to multiply and divide in rectangular form. So if I were to multiply two numbers, 2 plus 3j by 3 plus 4j, for example, I just multiply out the brackets. 2 3s are 6, 2 times 4j is plus 8j, multiplying every term in one by every term in the other. 3j times 3 is 9j, and 3j times 4j is 12j squared. Collecting like terms, 6, 9 and 8 is 17j plus 12j squared. But remember, j squared is the square root of minus 1. So, sorry, j is the square root of minus 1, so j squared is minus 1. So I can replace j squared with minus 1, which effectively changes the sign of the last number. And that always works like that. If it's negative, it becomes positive. If it's positive, it becomes negative. So we end up with this. Now we've got 6 minus 12 is minus 6 plus 17j. And that would be my final answer, multiplying numbers together. If I was dividing, I would have to do something slightly different. So dividing complex numbers, I would have to 3 plus 4j divided by 2 plus 5j, for example. I would multiply top and bottom by this bottom one here, written exactly the same, only with the sign change. Call the complex conjugate. So I'd multiply by 2 minus 5j, top and bottom. I've not changed this actual division because I could, if I wanted to, cancel these out and I'd be left with what I had in the first place. But there's a reason why I do this, and that will become obvious, hopefully. So this equals 3 plus 4j times 2 minus 5j all over this bottom bit. Now, it always turns out to give us the same answer, and that is the 2 squared, which gives us 4, and the 5 squared, which gives us 25. It always turns out like that. So you just square the 2 and square the 5 to get 4 plus 25, which is 29. And the reason why that works is, when we multiply this out, we get 2 times 2 is 4. And then when we multiply 2 by minus 5j and 5j times 2, they actually cancel each other out, which is why we do it. And then we end up with 5j times 5j gives us the 25 minus 25j squared. But remember, j squared is minus 1, so that gives us plus 25. So that's where these two come from. And it always works like that. And that's why we do it, because underneath we've just got one number. So we can end up with this all over 29. And now we just multiply out the brackets like we do for multiplication, and then divide the answer by 29. So that's going to give us 3 2s are 6, minus 15j plus 8j is minus 7j. 4j times minus 5j is minus 20j squared, which gives us plus 20 all over 29. And now we can add the 20 and the 6 to get 26 minus 7j over 29. At this point, we can split the fraction. We can call it 26 over 29 minus 7j over 29. So now we've got our two parts, the real part and the imaginary part, and all we do is work out what this is, and that's our answer, which comes out to be 0.9 minus 0.25j. So that's our answer. And if we could check this was right by converting to polar, this answer to polar, and then doing the polar division by converting each of our original complex numbers into polar form and doing the polar division way, and in that way we could show the two ways give the same answer. So check, you can add, subtract, multiply and divide complex numbers in both ways.